All right, good morning, guys. Today we're going to talk a little bit about the evolution of stars. Here's the outline of this lecture. We'll cover the star life cycle, the star termination, and also stellar recycling. So let's take a look at what we've got here. And let's start off talking a little bit about the star life cycle. I'm a little tongue-tied this morning. And if you read lesson 3 and did the Cornell notes, you'll know that stars generally are born in a nebula, which is, of course, a cloud of gas and dust. There's a picture of one right there. And essentially what happens is this dust and clouds right here, as gravity pulls on it, it really pulls on the denser particles that are in there. And what happens is it does that, you get the birth of a protostar. Further contraction happens where it pulls in closer and closer. You know, things pull in when they contract and they push out when they expand. But when they contract, it gets very, very hot and ends up blowing out the surrounding gas and dust around this area right here. And what you get left is, it's all stripped away, is a visible star. When the star starts fusing hydrogen into helium, it falls into the HR sequence, a main sequence star, like you guys drew up and did a pretty good job with. When the hydrogen gets all used up, it does leave the main sequence. It could, go the route of a giant red, or it could go a white dwarf. Massive stars become a red giant and cycling several times near the end of its life. And what they mean by that is it goes through a series of contracting, expanding, and repeats itself over and over again. Now, our sun, our star, is right on the border. It's really not a giant, and it's not a low mass one too. So towards the end of its life, it's going to go and turn into a giant red, but then it's going to switch back to a white dwarf. And this right over here, this is actually called the disk area, and this is what they call the jet. And this is particles getting blown out, and this is right before we would see a visible star. Just to kind of give you a little perspective here, this is what our sun looks like right now in size. And when it's towards the end of its life, it's actually going to expand to this size. Look at the size of this thing. This will be a red giant for a while. And just to give you an example of how big it is, it'll pretty much be the diameter of 1 AU, which is 93 million miles, the distance from the sun to our Earth right now. So that's going to happen for a while, and then eventually it'll become a white dwarf. In terms of the star termination, all stars are born in forms of in nebulae, but they die different ways. Average stars can't fuse elements heavier than helium. Stars with mass that are 10 times less than the sun become white dwarfs. Ones that have a mass that is 10 times greater than the sun become supernovas. Ours is right on the border right there, so it's actually going to, go the route of a giant and then become a dwarf. Did I mess that up? No, that's right. A supernova is a violent collapse of matter, protons, and electrons. What happens is there's such a violent collapse in the supernova that space between protons and electrons inside atoms actually leaves, and you've got protons and electrons slamming together and actually turning into neutrons, extremely dense. And this massive star collapse is creating a black hole. There's a video here to watch here. And a black hole basically is such an area of such gravitational pull that the escape velocity of particles, or even electromagnetic energy like light, is not stronger than the gravitational pull. So even if there is light that wants to leave, we'll never see it because the black hole, the gravitational pull, holds in the light energy. So let's check out this video. And you guys can watch that. It's pretty cool, showing the birth of a black hole. And we're going to move on to the next. Maybe I should play it too. Let's do that.
Star, a supermassive star that's 100 times the mass of the sun. At the end of its life, the core runs out of fuel. There's nothing left to hold it up, and the core collapses down into a black hole. When that happens, the enormous
Enormous gravity generated at the heart of supermassive stars runs wild. This is the dying star, VY Canis Majoris. It's more than 1 billion miles across. Like all stars, it's a giant nuclear fusion reactor, pumping energy outward. At the same time, the star's extreme gravity crushes inward. For a few million years, fusion and gravity are locked in standoff. But when the star runs out of fuel, fusion stops, and the stalemate ends. Gravity wins. In a millisecond, the core shrinks to a fraction of its original size, and a baby black hole is born. It starts to cannibalize what's left of the star.
As matter swirls into the black hole, it gets incredibly hot, and there are magnetic forces and frictional forces, and it's just a witch's brew, a nightmare what's going on right above the surface of the black hole.
The black hole in the middle keeps feeding on the body of the star around it. It eats the gas so fast, it chokes and coughs, blasting out huge beams of energy.
They basically eat their way out from the star. This happens in milliseconds. It happens before the rest of the star even knows the core is gone. And so basically, this star is dead before it hits the ground.
Finally, the star explodes. In 1 second, it blasts out 100 times more energy than our sun will produce over its entire life. What's left is a new black hole and 2 jets of energy hurtling through the universe at the speed of light. These jets are called gamma ray bursts.
They're incredibly energetic events. In terms of raw energy and power, gamma ray bursts are second only to the Big Bang itself.
Most of them last only a few seconds, and they fry anything in their way.
Very cool. All right, let's move on here. And let's talk about the last main point of this lecture, and that is recycling matter. And I've got a video right here on a planetary formation, but we'll go through this first. You'll see a couple things that are probably familiar with you. Gas from a terminating star does get recycled into new stars and planets. White dwarfs cast off, recognize those chemical symbols right there, hydrogen and helium, and these elements become part of what they call a planetary nebula. Now, hydrogen and helium are in the planetary nebula. They can form new stars, but not planets. And you're probably wondering, well, they call it a planetary nebula. Why not? Well, earlier astronomers, they called them planetary nebula, but probably should have called them something else. So cast-offs from white dwarfs can help form stars, but not planets. Supernovae, which is plural for supernova, more than one, produce shock waves that are so powerful that they push gas and dust in space, and basically kind of push it all together. And I'll tell you this right now too also, any elements that are in outer space that are heavier than hydrogen or helium, like for instance, I've got in parentheses there, carbon, silicon, and oxygen, any of those elements heavier than the others were created as a result of supernova. Gravity clumps the matter in nebulae to form stars and planets. So gravity clumping together this dust and matter that gets formed in nebulae do end up forming stars and or planets. Let's take a look at this video.
The places where stars and planets are born are among the galaxy's most beautiful locales. These cosmic landscapes change as new generations of stars light up and disperse their birth cloud. But the youngest stars seen here are already perhaps 1,000,000 years old, hardly toddlers.
Stars and planets form in the dark, inside vast cold clouds of gas and dust, such as these pillars imaged by the Hubble Space Telescope.
The dust is so thick we can't see the infant stars inside, at least not with visible light.
With infrared light, Hubble can see through all but the thickest dust. Yet it's in those dense knots that the youngest stars are forming.
To peer inside them, astronomers need the James Webb Space Telescope.
With a mirror larger than Hubble's and performance optimized for the infrared, Webb will give astronomers their closest look yet at stellar birth.
We're flying through a computer model that represents astronomers' best ideas about the star formation process.
Reddish colors indicate thicker dust. The temperature, less than 400 degrees below 0 Fahrenheit.
Or less than 240 degrees below 0 Celsius.
That pinwheel ahead is a protostar, perhaps 10,000 years old. Protostars arise when a dense knot of dust, less than a light year across, collapses. But the details of the process are not well known.
Elsewhere in the cloud, another protostar is preparing to build planets. As the cloud that created the protostar collapsed, it flattened into a disk. The disk we see here is 600 times the size of Earth's orbit around the sun.
If placed in our solar system, it would extend far beyond the planets.
In this computer model, the disk continues to accumulate gas and dust from its surroundings for thousands of years. Eventually, the disk fragments, producing dense, bright structures. These may become sites where giant planets form.
Later, during another phase of construction, smaller Earth-sized planets may take shape.
At least, that's what scientists think happens. It will take the Webb telescope's keen infrared eye to see what's really going on in the cold heart of stellar nurseries.
Very cool. All right, so in summary, we've talked about the star life cycle and how while all stars are born in nebula, they do die differently. They end their lives differently depending on whether they're a giant, supergiant, or whether they're like a small average mass star or a low mass star. And also that at the conclusion of the star's life, the matter that's released does get recycled, whether it's matter that's from a white dwarf that can be used to make other stars, or from the result of a supernebula that could form other stars and/or planets. Down at the bottom, I've got there, it says, add this question, so this will be question number 9, to the questions on the attached worksheet. There's an attached worksheet that you'll see. And so add this question to it: how are supernovae important in recycling matter in the universe? Okay, take it easy and have a great day, guys. Bye-bye.